Alright, let's see. I should be streaming live, I guess. Seems to be working in one part of it. I don't see any image yet on YouTube. So, there we go. Alright, so now I know it's working. So we have a mindless marbles video I didn't see. Okay, so 8 days ago or something. And, you know, it's just another piece of crap, okay, just thrown in here to be noise. So instead of dealing with the actual subject and you know, the fact that if you conserve momentum using a lever, as you must, you're obligated to create free energy by the kinetic energy formula. That's how really bad their formula is that it's that impossible to evade the problem. And we want to erase part of this because I have my notes on here. Important stuff. Blah, 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 blah. Alright, so he's done this little stream of experiments. So it's supposed to be a lever, but it has this stupid pendulum hanging out the bottom for I don't know what reason. And then as his quick release, okay, get this, he's using a book. So the quick release, he's taking the normally semi-quick hand, and he's picking up something heavy to do a quick release, right? So it's just kind of funny. That, yes, he'd be much better just sliding his finger off the end of the stick, and that would be much, much quicker. But he doesn't even know, he can't even engineer that simple fact. Can't figure that much out. And yet he's an expert on, you know, these motion dynamics. Alright, so he does the lever with no weights. You can see that, I hope. Let's go see if you can see that. No, you can't see that. So there you go. I probably should just zoom in on it. That's probably what I should do. Alright, and he's just going to count how long it takes for it to oscillate. Alright, so I think that's what's... Okay, so now we have weights on it. So he does it without weights, and it comes out a number like 17. And eventually he will do something here. Okay, he puts a book on it, as you see. Alright, so, and then it oscillates. And what he's doing is counting how long it takes it to oscillate 10 times. Now, what this demonstrates, I don't understand entirely, because all it could really demonstrate is that the speed of these things has sped up or slowed down, but it can't change the fact that these two objects have to be moving the same speed. I mean, if I put something twice as far out on a lever, it has to still be moving twice the speed. So it doesn't do anything except say somehow there's more or less energy in the system. And that's what he should notice, is that what's the difference, you know, when I do this experiment and I put two heavy masses here, or I put one heavy mass out here. The difference is it's not the same amount of energy you're putting into the system. One mass out here, okay, is less energy because it's not 4 times higher. To get the same out of gravity, right? The whole theory, the whole point, the whole argument is this one twice the velocity in free fall, it has to go 4 times the distance to acquire that. Well, the same truth is still the truth because the lever's doing the conversion. So the lever is going to create the same energy in the shorter fall, but it can't, obviously it can't create more gravitational energy. The fact is you just haven't risen the one mass 4 times higher than the 2 mass. So the system as a whole will have less energy. It's a balanced system, but it has a certain amount of weight in it. And you're putting a certain amount of weight up in gravity, and that certain amount of weight applies a certain amount of pressure. So you're varying the amount you're putting in because you're not taking a balance and then injecting energy. Alright, so this is the part where I should draw the difference between this experiment and Brozo's experiment. And just to point out and illustrate how this isn't a consistent amount of energy. The two circumstances he creates aren't the same amount of energy because he's not putting new energy in. He's using the gravitational positioning of the weights as the energy source. So he's going to get a difference because of that. Alright, so lever. So we'll do Brozo first. And it's pretty conclusive evidence. Okay. So 2 mass, you put a 2 mass here, and it goes 1/2 the speed. So you do the experiment, same compression of the spring. So you compress the spring the same amount for both experiments. You compress it to, say, this distance. So you move the lever here, and you put a 2 mass here, and you get a speed. And then you put a 1 mass out here, and you get a speed. And this is obviously twice the velocity, okay, that this goes. All right, he got numbers 19 and 11, pretty close to 2 to 1. So this is Brozo's experiment, the ones you got to duplicate or prove broken, okay, because it basically proved the point that the same force, okay, produces 2 different amounts of energy. And in this case, twice as much energy over here. Okay, so I just put the mass further out. I get twice as much energy out of the same spring compression. Doesn't make any sense. Isn't a conservation of momentum, because I would compress the spring by dropping the masses, and obviously I would drop this one from 4 times the height, and I would drop this from 1 unit of height, and I would compress the spring the same amount because it's a weight. All right, so they haven't fixed any of this. So this new experiment, he's taking the lever, and he's doing it with 2 masses and 2 mass. First he does it with nothing. Okay, so nothing on the lever, gets a number like 17. Okay, no weight. So he just lets it oscillate. But it has this pendulum, which I don't know what purpose that serves. So I don't know how much weight that constitutes. So that's going to dampen its motion. Okay, and then so he does the experiment with 2 masses in these locations. All right, and then he does the experiment with a 2 mass here and a 1 mass out here. They should be equal. So, you know, but the trick is, right, what's the difference between the 2 mass here and the 1 mass here is that I'm not going to go 4 times higher here into gravity. I'm not going to go the necessary extra amount in gravity to create the extra pressure or weight. So in a sense, the 2 mass risen 1 unit of distance height is more energy than the 1 mass risen 2 units of height. Raising the 1 mass 2 units of height isn't the same amount of energy as it is raising the 1 unit of height. So it's because it's about velocity. The velocity is what's compensating for the fact that the masses are different. So the amount of energy you're putting into the system is different. So if you had flipped this experiment the other way, that is, if you had the 2 mass over here and the 1 mass over here, then he would have been putting the same amount of energy into the experiment. But he didn't put the same amount in. He put a different amount in because this wasn't here, and he just had a 1 mass twice the height instead of a 1 mass 4 times the height. So he didn't put the same energy into the system. That's why he got a different timed result. So with the 2 masses together, 2 to 2, okay, it was like 25. Let me see, I can look. All right. Yeah, 25 something or other. And then with this configuration of a 2 mass here and a 1 mass out here, you got 28. So it's not much of a difference, but it's a difference. And then with 1 mass and 1 mass, you got 31. So not terribly significant difference here. I mean, that could just be, you know, fudges in having these placed in the right locations, and also whatever this influence is. I can't rule it out as being a changing the balance between the 2 objects. So if you get rid of this stick, you're getting rid of something that's breaking the lever. It's causing it to have, it could be causing it to have to be more weight on one side than on the other side. Okay, so it could be imbalancing the lever, which would also be a way of destroying the energy and therefore having slower oscillations in the future after the first oscillation. So anyway, these 2 numbers are close. Okay, this one's pretty distant, but that's the radical change from 2 to 1. Okay, meaning that you didn't raise the mass twice as high. And so that would be accounting for that difference. So it's a pretty easy thing to figure out that the whole idea is to have the balance and then put a fixed amount of energy in, not to or to drop something, okay? But there's no point in doing the turning it with weights on it already, because that means you're putting a different amount of mass up in gravity. So for the one mass further out, it's a different amount of mass up in gravity. It's not the same gravitational potential energy because it's not the right height. Yeah, that's pretty much the answer to it. Alright, so I got here because of the Iron Gosling guy, the asshole. Look, if you want me to unblock you, it's okay. I'll unblock you, but you have to give me a link to your channel. Because frankly, oh, here it is. Okay. But you know what for? Do you really think you can sit there and temper your exaggerations and your lies? I'm not sure you can. Dear mindless, I mean, this is, you know. Do you know if Draft has seen or commented on this video? I feel it's very important. Ain't that he should. So I don't know what that means, but whatever. And then Brozo says superb, even though it kind of debunks his own video. So, and it's superb at what? It's again just creating noise, okay? Pretending this experiment is saying something. So Brozo did an experiment where he called it a trebuchet, right? And it didn't have any gravitational mass. It was a catapult, okay, just using a spring moving the whole, just one side of the lever. There was no counterbalancing side on the lever. So I mean, these people can't really do the experiments that need to be done. They have to keep rigging and gerrymandering peculiar experiments. Because if they just did the simple thing of recognizing that, all right, if I have to conserve momentum and I look at a lever, I know that's what it's doing. It's conserving the momentum. So it's taking energy from one object and giving it to the other object, and it doesn't matter that they have uneven masses because I put them in a place that fixes that. That makes it possible for the deceleration in one place to equal the acceleration in the other place, and I've essentially created a Newton's cradle. And so I really can't get out of the simple argument that it's a fact, okay, that if I could make a Newton's cradle and have twice the mass hit and one mass leave, that it's going to leave with twice the velocity, not 4 times the velocity. And that's just a fact. Okay, so you're broke, you're out of luck. There's no way you can fix your free energy theory. It's a free energy theory. Anytime you convert energy from a heavy object into a lighter object, you will create free energy by your theory. And anytime you convert the energy from a heavy object from a light object into a heavy object, you will lose, you know, tons and tons and tons of energy. The theory is nonsensical. And the fact that you will not address these arguments is just proof of your gross insincerity in this conversation. Alright, so there really wasn't nothing there. So they had 8 days to comment. This is the best they could do. Yeah, pretty surprising. So, alright, so then we'll go to the comments on the message board. Not much there, but we'll do it anyway. So I don't need this at the moment, and then I need to resize that, so I'll fix that. I made it monstrous. I don't need it monstrous. Alright, so let's go to Gosling's comment. Alright, let's just see if there's any new ones. Okay, none. Alright, blah, 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 blah. Alright, yeah, so I'll go to your channel and unblock you, but I don't see the point, frankly. Alright, it says here, so it's very hard to help you as you are a bit thick. So again, I can't spell out these arguments. I've been spelling them out over and over again and asking you to please just answer the question. Do you really think that if I throw 2 liters of water out the side of my spaceship at 1 mile an hour, and then I shoot at 2,000 miles an hour, okay, 2 liters, that's, you know, 2 kilograms, and then at 2,000 miles an hour I throw 1 gram, right, 2 grams, I shoot it out at 1,000 miles an hour, that somehow my spaceship is going to radically turn? So again, if I shot a bullet into a gun, I would have 2,000 joules of energy in the gun. It's what you actually think. The gun is going to move with 2,000 joules of energy. It's going to absorb 2,000 joules of energy, and it's going to move dramatically more than the recoil of the gun. The recoil only has 2 joules. When the bullet hits, there's going to be absorption of 2,000 joules of energy. Do you really think that's going to happen? I mean, yeah, whatever. I've drawn it so many ways. What, you don't understand the friction argument? You really think friction is always the same? And you really don't pay any attention to the fact that, I've made all these arguments about how gravity is about time. MGT, not MGH, MGT, how long you're in the gravity. I mean, I've pointed out in the friction argument that, with rolling friction, an object doesn't go half the speed until it goes 3/4 of its traveling distance. So it travels 3/4 of its traveling distance before it's going half as fast. That doesn't indicate to you that it can't be possible that losing the same amount of energy, no matter what speed it's going at, it's clearly, obviously losing less energy when it's going fast than it loses when it's going slow. You can't understand that argument? You're so fucking thick. I mean, it's just amazing. You call me thick when you can't respond to a single one of these points. Alright, you could easily debunk your Lieberman's. Oh, we already did this twizzly crap. Yeah, so anyways, yeah, it's just too silly. Way too silly, frankly. Alright, so we're done with today's adventure. I have a whole other argument about relativity, and there's videos just so aching to be played, so maybe which one should I deal with? I mean, I got into a bunch of, somebody dropped a name, and so this Tim Maldulin guy, and then that led me to this other guy called what's his name? Where is it? Okay, I know it's here. Adam Becker. And they're all hyping this, it's just disgusting, quantum mechanics is most proven history, blah, 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 blah. But the good news is it's a whole explanation of Bell, and I ended up seeing a little clip of Bell, and he was pretty unpersuasive as a speaker, frankly. Apparently his book is, brilliant, but he wasn't too good at presenting his arguments, frankly. So I'm looking for a free version of the book somewhere. So if somebody knows where that is, I'd appreciate it. And then there's this Brian Greene video that's just insanely silly. I mean, I really want to play the whole thing. So maybe I'll do some of it in this video, and I'll just do it over in numerous videos. I'm only halfway through it, and it's just such a pile of crap. I'm just amazed that people fall for this shit. It's just such garbage. It's so irrational, so illogical. What the hell is wrong with the shape of this thing? I don't know, it's not quite right, but see, can I change anything? Yeah, I can change it a little. No, I can't change it much. The YouTube's still there. It's cutting off the bottom of the screen. I don't like that much. I don't want to go fixing the settings, so you'll have to live with it. Alright, so let me put the little chat crap thing in here so I can see that while I'm doing this other crap. So it's not connected, so it's called, from what I recall, it's just called, oh, I haven't popped it out yet, so yeah, I can't find it until I actually pop it out. Oh, okay. There's a catch to it. Alright, pop out chat. Good enough. So nothing in it, which is about average. Alright, now I probably have to switch things. I probably have to go to something else and then come back to this and then do the property thing and see if it's there. Yeah, there it is. Okay, that should be it anyway. So I can make it visible. Didn't make it visible. Oh, it's behind the other thing. Yeah, there it is. Okay. So many little details. Alright, so let's move this. Oh, no, I don't want to move that. I want to move this up. And then I can move this over. Oh, fuck, I don't want to move that. There are some pretty irritating features of OBS. You know, it does some things that just aren't very helpful in terms of trying to get things moved around and clicking on the right object. But anyway, just complaining, which do a lot of. All right, so we'll do some of this Brian Greene crap. So we'll start from the beginning, but he is just so
compared to others, that depends on the relative speed between.
So animated in everything he does. All right, it's just whatever. All right, we don't need it that fast, so I'll play it and see how much faster can I play it and get away with it. Let's try twice as fast. I think you can follow along. It will just make it more tolerable for me, frankly.
Missed through our everyday experience. Why have we missed it? I mean, why aren't we aware of special relativity right in our bones? And the answer to that is, when we look out at the universe, we recognize that there are a huge range of scales that constitute reality. And we humans only have access to a very small part of that totality. So to give you a feel for that, let's look at one axis, a length axis. And if you look at
so this was kind of a boring bit, so we can probably get through this. I didn't even image this very well in terms of demonstrating the huge difference between the size of an atom and the size of a human. Clearly, all right, through all of our tools, we're quite capable of seeing an awful lot of little things and awful big things, okay? We can see galaxies, we can see monstrously huge things. So to say we don't interact in a much bigger world than just our material size would be kind of just cheating the argument, and of course he cheats the argument. Okay, so let's jump ahead to somewhere in here. So scale is kind of, yeah, it's really interesting, but know what the most important feature of scale is that the little universe is the real universe. It's the one in the real empty space. It's the one doing all the work. It's the one the place everything happens. And we're in the really slow, clunky verse compared to the real universe. So for every word I just spoke, if you thought of those words as footsteps, right? Like every atomic particle moving was one footstep. You know what I mean? It would be thousands or millions of years worth of footsteps that took place just to make me say one word. So if we were little people on the scale of the atom, millennia went by in the time I said the word millennia. Just in the amount of time it took to say that word, centuries and centuries and centuries of time went by if you were somebody living on an atom.
We humans only have access to a small piece of the totality of what's out there. And therefore, it would be surprising if...
Oh, I really should enlarge him because he's just so funny. Oh, he's so... Everything has to be dramatized.
What we have experienced really does tell us about the physics at all possible scales.
It's just like a pantomime physicist. He's like pantomime physicist. He's just, he's got to somehow with his hands illustrate every point. Somehow he has to make it visual in some way or another.
In length, in speed, and in mass. And it turns out that indeed it is the case that when you look at extremes...
I guess this is sort of a cliche, right? I mean, it's Jewish, and so there's a little bit of a joke in this. Nothing anti-Semitic, just saying, it is kind of a cliche.
Of mass, or length, or speed, the world operates, the universe operates in ways that we are not accustomed to.
Even his, he's got his feet, and he's bouncing, and his knees are, he's like a professional athletic pantomimer.
If you are looking at extremes, say, a very small size, the new physics that comes into play is called...
The new physics, right? It's just the new religion. It's not physics. It's not about anything physical. It's about a bunch of wooey mush.
Quantum mechanics. If you are looking at extremes of huge mass, the new physics that comes into play is the general theory of relativity.
And the general theory. And then there's that special one that doesn't mean much. Except if you're in gravity.
If you are looking at extremes of speed, how the universe behaves at very, very high speeds, then it is the special theory of relativity that comes into play. That is what we are going to be discussing.
It's actually the same theory. So my argument would be, that all that gravity's giving you, is velocity. That's why you have momentum going into the earth. That's why you weigh something, is because gravity gave you a velocity, and you now have momentum, and you have weight, because you have a velocity and a mass, and that's weight. I mean, it's not that complicated, frankly. And so things in heavy gravity, it's like going fast, because actually you are going fast. Because you keep going down into the earth, and the earth keeps pushing you back up, and you keep going down, and it keeps pushing you back up, and it's doing it so fast that all those little jiggles add up to an awful lot of distance.
So in a nutshell, all of the discussion we are going to be having here is focused upon how the universe behaves at very high speeds.
Okay, but it's, bullshit.
That is the special theory of relativity.
La, 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 la.
Since speed is the fundamental core of what...
All right, so it's velocity, right? Speed is just kind of a child's term. You really shouldn't use that term in physics.
Drives the special theory of relativity. Let's start at the beginning and ask the most basic question of all, which is, what is speed? Well...
Yes, it's just how much distance you traveled in how much time, right? So that's how you determine it. And the distance, I would argue, is in real space. Now, they don't think space is real, so it's almost silly to talk about it. But as I would point out, through what I've drawn over here, is there's this fact about how things bang into each other. And you can, in fact, tell who's moving and who's not moving by simply banging uneven masses against each other. It works. If I bang a light object into a heavy object, if I give the light, say if two things are heading for each other at 10 miles an hour, if I do it one way, where the heavy object's going 10 miles an hour, there's more energy in the system. So just like this lever argument before, I've put more energy in the system by having the heavy object go 10 miles an hour. If the lighter object is going to 10 miles an hour, there's less energy. So when they hit, they will move away from each other at a different speed depending on how much energy was in the system. And the fact is, the more energy, the slower they move apart, and the less energy, the faster they move apart. And that's the little nuance to it. But you can tell the difference. You can test for it. The fact that you can't test for it sitting in your chair, right, you can't do it that way. But you can test for it by giving your condition to some other object and then allowing that object to do the test. And you'll know whether you have velocity or not. Yes, you can look out the window and see if the rest of the universe is moving, but that really isn't a good test because the rest of the universe really could be moving very fast past your window. But this weight test, you can't defeat. It'll always work.
Oh, know the answer to that, but let's get all on the same page. So if that car, say, has a speed of 100 kilometers per hour, we all know what that means. If we look at how far it's gone, divided by how long it takes it to get there, so let's say this is 1 hour journey. If it's going 100 kilometers an hour, we know that it will have traveled 100 kilometers in that hour.
Okay,
that's what speed is. So in essence, speed is nothing but distance that an object travels divided by duration. Now, expressed in that language, speed...
Duration, is a trick word, right? Why you chose that word? But anyway, no, it's clicks of a clock, and so yes, that's the whole game. And we have standard clocks, and the whole reason why we're using a clock is because clocks work, not because clocks don't work.
Speed might seem like, I don't know, a kind of boring concept, a pedestrian concept. Why concern yourself with speed? The answer to that is clear if we recognize that distance is a measure that has to do with space. Duration is a measure that has to do with time. So if we...
So he's just finding an excuse to put space and time together, right? It's really not space. Distance isn't space. It is measured in any kind of... You can measure the distance of a line. You don't have to measure space. So it's just playing games with the words.
We find, as we are going to find going forward, that...
I mean, you could say separation and time. You know, there's lots of different words you could use. So again, just playing a word game that ends up being a math game.
Speed has unusual features when the speeds involved get very big, near the speed of light, what we really will therefore be learning.
Ah, yes, really, 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 we will be learning it. Really, really.
Is that space and time have weird, strange features. That is what?
All right, so that's the whole point, right? That's my whole objection. That's Einstein's whole objection. Why do they have to have weird features? Yes, there's some phenomenon that you might not have an instant answer for. It's not obvious, the little catch, the little nuance. And I've already explained the two-slit experiment in so many ways, so many times. And you can see the obvious mistakes made where, they're only describing with their mathematics a very rare two-slit experiment. Just one tiny one where the slits happen to be so infinitesimal there can't be any constructive or destructive interference between the two surfaces. There's not enough distance between the two surfaces to even create any constructive or destructive interference. So they can't be a source of any interference as individual surfaces. So into that special case, and what does that special case mean? They turned a four-surface experiment into a two-surface experiment. They converted the two-slit back into a single slit by destroying two of the surfaces as being relevant. That's a factual explanation of their misunderstanding. And that misunderstanding is the source of all of this woo.
We are after. Okay, good. That's where we're headed.
And they'll just keep saying, we've already proven this wave thing, we've already proven all of this crap, and the proof is weak and thin and, superficial. It's an incredibly superficial proof. And yet they hype and push and declare. And the simple argument is no, I think there is real space and real time, and I'm not at all confused into thinking they don't exist, just as Newton, Descartes, and Galileo thought they existed. You really don't need to play this game that they're not real things.
Let's start by
real conditions. It's a real condition that there's emptiness or space between two objects. Obviously the space isn't a something, but the fact that there is distance is a something.
By first thinking about the non-strange features of speed, the features that we all hold in our intuition. So what are the basic features of speed? Well, first off, speed is a concept that even before Einstein was known is a concept that is relative. What do I mean by that? Well, imagine we look at this car, say it's going 100 kilometers per hour. What we need to say is 100 kilometers per hour relative to the road. Why?
So we don't have to do that. So that's the whole point. We can understand ahead of time that the air is filling up square feet of space, that the space out in the space is square feet of space. There's a certain number of feet to the moon, that everything can be measured in some kind of way, and that all we have to do is really measure how many of those squares, is it moving relative to a fixed square. So I just create a fixed square somewhere and I just measure how far it travels from that fixed square.
That road is itself moving. Let's say it's on a boat, the boat is moving, then the car's speed relative to the water is not 100 kilometers per hour. And if we zoom out and look at that car on the surface of the Earth, and we realize that the Earth itself is spinning around, the Earth itself is going in...
Right. So none of this stops us from understanding exactly all of these facts, that we have a bunch of compound motions, and that in our experience, we're just really going to see motion when two objects have some different motion. If we both have the same motion, it's not going to look like motion, because we're both moving in the same direction, doing exactly the same thing, so there's not going to be anything to distinguish one from the other, because they're staying exactly the same distance apart and doing the same thing. But I can already understand that. I can already understand I'm being pushed into the ground by gravity. I don't see it, but I can understand it's happening because I can feel the ground pushing me back up. I mean, so this isn't beyond our capacity to understand, but we don't, there's no need to say this special word relativity and pretend relativity means there's no absolute space and there's no absolute quiet. There's something in space that may have no velocity in any directions.
Orbit around the sun, with respect to the frame of reference, our perspective right now, that car is executing a pretty complicated motion, not just 100 kilometers per hour. So it's always vital when you're talking about speed to recognize that you can only ever frame the idea of speed for ordinary objects that we encounter as the object has this and that speed relative to this or that object.
So it's not really relative, it's compared to. You're just making a comparison, and there's no comparison to be made if they're moving exactly the same. Is the point. And so you're just looking for differences between objects. And you're going to understand that you have a lot of differences between you and, say, the moon, but there's not so many differences between you and the desk or your computer.
You need to specify the reference in order that the speed that you are specifying has any meaning at all. Okay, so that's a very basic feature of speed, that it is relative. Another basic feature of speed is that it is additive and subtractive. So what do I mean by that? Well, let's imagine that we have two characters who are playing a game of catch with, say, a football. George and Gracie, two characters that we are going to encounter often in our...
So this is true for material objects. So material objects are different than forces. Okay, that should be distinguished, but he's not going to make that distinction. He's going to pretend they're all behaving the same way when, no, they don't behave the same way.
Our discussions, and imagine that they're throwing that football...
They don't function the same way.
...back and forth at, say, 5 meters per second. Now, that's all well and good, completely understood, but let's imagine that they go out to play a game of catch on another day, and Gracie is surprised to see that George has a hand grenade.
No, this is kind of, you're just like, why did they go here? This is kind of silly. They could have just said he springs on a board or something and adds some velocity while he throws the ball, or he falls down as he throws the ball.
Now, she doesn't like hand grenades, and so she runs away when he throws it because she knows that by running away from the hand grenade, she can change the speed at which it approaches her. She can subtract her own speed from the speed of the oncoming grenade, and that way have it approach her not, say, at the initial speed at which it was tossed, which, for instance, might be just...
So again, it's all about somebody's perspective rather than the actual speed something's traveling. So it's not like it was thrown any faster. It's not like it's moving any faster. You're just saying, well, I'm just going to say because I can be moving towards something or away from something, I'm somehow changing its speed. That's where they want to head. And it's so obvious that that's where they want to head, that somehow I'm changing the physical fact. So he's going to sit there and tell us how fast the football is moving when it's not moving that fast. It's moving the same speed he threw at the football. You know, the grenade was moving at the same speed he threw the football at. It's no difference. And the fact that she's running away or running towards doesn't change it any. So again, this is how they destroy all kinds of rational physics, is they pretend that somehow the receiver of a radio signal can somehow change the show that's being broadcast. And it can't do that.
Like the football, 5 meters per second. Instead, if she runs away at 3 meters per second, she knows that now the grenade will approach her more slowly at 2 meters per second. And that is a good thing when it comes to hand grenades. Similarly, it's the case that if an observer like Gracie is to not run away, but say run toward an object that is being thrown at her, the speed with which she approaches the object will be added to the rate at which it approaches her. So if it was thrown at 5 and she's running toward it at 3, well, we all know that that means it will approach her at 8.
Right, so it doesn't move at 8, just like light doesn't move at 8. So if I run towards light, I'm not changing how fast the light's moving. I'm just changing how much distance the light has to travel to get to me. And it's just a fact. And the same thing is a fact here. You're just changing the amount of time, the distance the thing has to travel. It travels less distance, then it's going to be less, it's going to seem faster, but it just seems that way. It didn't go any faster. You just shortened the distance it had to travel.
Meters per second. Speed is additive and subtractive. You can change...
All right, so, obviously everything's additive, subtractive. Let's see. What is this? What is... Oh, okay, I see. Okay, that's your title. Okay, so it's Amanda, I guess. Yes, physics. I'm live doing physics, but no one's participating, so that's okay. Fewer comments. I mean, the first rooms I did, there seemed to be some engagement, but it's kind of died off the last few videos. But I'm thinking that might be Google. I think Google is not, announcing as it used to.
The speed with which an object is coming toward you by either running toward it or away from it. Now let me quickly mention, just as a small footnote, these basic calculations that we've done here, we surprisingly are going to find that they are only approximate when you take into account some of the strange features of relativity.
All right, so obviously that's just so bullshitty, right? You know, that you're going to change the numbers in any significant way with your stupid woo physics. Oh, it's just, yeah, just such a joke. We add gamma, you know, it changes the 10 to the 47th decimal.
But that's something that we will encounter later, especially if you're doing the math version of this course. But in terms of the basic idea that comes from our intuition, you certainly would anticipate that if you run toward an object, its speed will approach you more quickly. If you run away from an object, it'll approach you more slowly.
So again, it doesn't approach you any quicker or any slower. You're just creating more or less distance for it to have to travel. So it'll take longer to get to you, or it'll take less time to get to you. And the same is true for light. If I run towards a flashlight, I'm technically going to get to the photons sooner. And if I'm running away from it, the photons are going to get to me slower. It'll take longer.
Third basic feature of speed that, again, we are all familiar with is this. When you are executing a very special kind of motion, what we call constant velocity motion, motion that has a fixed speed, fixed magnitude, and a fixed direction, then you can't feel that motion, right? You can't feel that motion for a very good reason. If you are executing constant velocity motion, you are completely justified in claiming to be at rest. And
all right, so yes, so once you're up to a speed, that means all of your pieces are moving at that same speed, so now there's no differences, so you can't feel any tugs or pulls or discomfort. And everything else in the room is doing the same thing. We have now propelled everything, given it all the same velocity, and so it's perfectly comfortable because there's nothing different. And it's only when we introduce something different, like a chair, okay, in the case of gravity, that all of a sudden, shit, I can't keep going anymore. I have to hit the damn frickin' chair. So gravity is giving me a nice constant velocity, and the chair is interrupting it.
The rest of the world moving by you. In that sense, constant velocity motion is very special because it is motion that is completely subjective. There is no absolute notion of being in.
All right, so there's no reason to say that. There's no absolute notion. You still have a velocity, and the fact is that it's doing something to your matter. And if you really think about it, you could understand that the faster and faster you go, that the little electrons and protons and all of that stuff, they're all doing complex motions, you know, inside your body. And those complex motions can't make them go faster than the speed of light. So those motions are going to get very screwed up the faster you go. Just like if there was a bird flying in a bird cage and I move the bird cage, the bird has to fly longer this way and less this way to stay in the cage going in a circle. The circle gets elongated based on my velocity. And that will be something you could visually see. You could visually do the experiment and see that, yeah, the bird has to fly this way a lot longer than it has to fly that way. So it's not like I can't see any of this happening to things. You can see it. You just have to provide an opportunity to see it. The right, take a bird with you, so to speak.
In motion when the velocity is constant. So let me give you a quick example of that.
It's probably not a perfect example because once you're at a constant velocity, the bird, okay, is also already at that constant velocity, and so it's already built into the mechanism, you know, that it's going to be going that way constantly. Without even flying that way, it's already going that way.
So let's imagine that we have one and the same physical situation described from two different perspectives. So what I'm going to imagine is having George and Gracie floating in space, okay? Floating in space. Now here's George's view of the events. He looks out and he sees a character, Gracie, coming toward him, and she waves as she passes, as does he. His perspective is that he is stationary and she is rushing by him. Good. Now I'm going to show you exactly the same situation, but from Gracie's perspective. So what does Gracie say? From her perspective, she says that she is stationary out there in space. She looks out into the distance, and she sees George rushing by. He waves. She does too.
Right. So what? Yeah, I mean, we can understand that, yes, you can't tell if you just look out the window. You need some other reference to tell you if there's two things passing each other. Because, yes, it could just be you going the full speed, or they're going the full speed, or you're both going 50-50. See, this could mean that she's going half that speed and he's going the other half. So there's three options. There's not just him racing by her or her racing by him. There's all kinds of percentages. He could have 1/3 of the velocity and she could have 2/3.
And he goes on his merry way. Is one perspective right and the other wrong? Absolutely not. You are completely justified if you're not accelerating.
So he's saying you're completely justified in thinking it is that way, when that's not what you're justified in doing. You're supposed to be smart enough to know that you have to do a test, that there's some other way you have to find out who's actually moving. You have to have some other reference, okay, that you're more certain about its condition to compare the things to. You have to do my test. So my test is a pretty simple test, right? It's, if I do this simple experiment of banging something twice the mass into something half the mass, if I do it this way, that is, I give this the mass, it has twice the energy, and this will reflect, and this will continue going this way, and they will separate. Okay. And then if I do it the other way around, this has the motion, and this is at rest, and I hit it. This bounces off, goes that way, and this goes a little bit forward. But the fact is the distance, the speed at which they change their position, okay, will be greater or lesser. So, taking all the relative conditions, all right, there's no fixed contact point that you're going to measure, so you're not going to really measure which direction anything's going, because something could be going slower. This could be spinning on the Earth at 1,000 miles an hour, and I could make it go 990 miles an hour. So it's actually going slower, even though it's going to look to an object like it's got a real 10 miles an hour, but it doesn't have any. But anyway, that test will solve the problem, because the two outcomes aren't the same.
If you aren't changing your speed or changing the direction of motion to say that...
And the third option of them both having velocities would also be a different number, a different amount of energy, and so you'll get a different solution. So all you have to do is put an object on each thing that's moving, okay, and then watch how those objects collide, and it'll tell you who's got the real velocity.
You are stationary. Now, the reason why I'm emphasizing constant velocity motion is something that you have all experienced, right? If you are in a car and you take a sharp turn, you feel your body being pushed this direction, you know that you are moving. If you are in an airplane and it's taking off, as it accelerates, as it speeds up, you feel yourself.
So you're really not being pushed in that direction, in the sense that your body just wants to go straight and there's nothing pushing you back in. So that's the catch. Your body wants to go straight, the car's turning. That's all that's happening. And so the car's pushing on you.
Pushed back into the seat, you know that you are in motion. But if you're not accelerating, you don't feel the motion, and in fact, there is no way for you to detect the motion at all. So for instance, if you imagine that George and Gracie were in...
So if you're not changing, you can't tell. But the fact is you can change, and if gravity accelerates you, you won't feel it. So if gravity accelerates, you fall, free fall, you're not going to be able to feel the free fall, except that you'll know it's different than when you're walking around in gravity. But the point is gravity is going to push you without you being able to sense how fast it's pushing or how much it's pushing or any of that stuff. You can't sense any of it because it moves every piece of your body at the same rate. It gives it the same speed. So it applies a lot of force to the heavy bits and a little bit of force to the light bits. It gives exactly the amount of force the mass dictates, and so it all moves the same rate. Every atom is falling at the same rate. So you can't feel your motion. The only time you can feel motion, detect it with your own sensors, is it has to be uneven. Like when the earth pushes you back up. It pushes your flesh, it pushes you in one portion of your body, and it has to be connected. The impulse, the momentum has to move through your whole body at a different, and it'll move through different parts at different rates, and it'll be very uneven, and you'll feel it. But the idea that you can never sense velocity isn't true, and the fact that acceleration doesn't always give itself away either.
Floating laboratories out there in space, and they do experiments to work out the laws of physics. They will work out exactly the same laws because they're...
No, that's only true if you're talking about objects that are stuck and can't be freed. can't be in any way liberated from the fact that they all have this common velocity. So, but like I said, if I allow something to interact with the world, that is, I just dangle one of these markers outside my ship, and I allow it to hit a marker on some other ship, that will tell me. As long as my piece is a different mass than its piece. As long as the two masses of the two objects I bang into each other are different, I'm going to get a different outcome depending on who's really moving. Because there'll be a real energy difference.
There will be absolutely no remnant, no experimental implication of their relative motion if that motion is at constant speed in a fixed direction. No way to determine your state of motion.
All right, and then there's the more, the Einsteinian, I mean, it's Einstein's own thought experiment. That's sort of a joke and an irony of the light clock. Is a way to detect. I bounce the light in front of me in a spaceship, bounce it back and forth across the ship, and the faster I go, the more the light will appear to miss the other side of the ship. It will start moving towards me, if it's in front of me, in the sense that the dot on the side of the ship will be in the wrong position. Now, it's, they're subject to a lot of qualifications, because you have to say that, okay, the photon has to be admitted as a whole object, but I could even do it with a physical object, because the motion, it depends on when I apply the motion. So if I apply the motion after I free the object, then I'll be easily to see that I'm acquiring motion. But if in the constant velocity way, the only way to do it is with something like a light clock. But then you have to have some control over how light is produced, because the fact is your emitter is also moving. So you have to create like a hole in the ship for the light to come through, so there can only be the one photon. And but the fact is if you do it, the light will miss the target, and that will be essentially a speedometer. The faster you go, the more it misses.
Because you are justified in saying that you are at rest. Now that idea that you can claim to be at rest, that there's no implication of constant velocity motion, does not start with special relativity. It does not start with Albert Einstein. This is an idea actually that goes way, way back. It goes all the way back to Galileo.
So it really doesn't, okay? Galileo's relativity was just a concession to this is the way it looks. He wasn't making some absolute argument about the fact that there's no absolute space or no absolute velocities. He was just saying the obvious, that when things are together doing exactly the same thing, you can't see any difference because they're doing the same thing. But if you give one of them some other kind of energy or influence, if you blend them with something, they'll change what they have, and there'll be a relative change based on what you influence, whether you take energy away or whether you give them energy in some direction, whether you influence them. So it doesn't have anything to do with Einstein's relativity. All right, nobody commenting. Interesting. Yeah, well, whatever. So I'm going to give out. I'll give you like the, I'll just do this segment, do the other segments in other videos.
And Galileo wrote a wonderfully poetic description of this idea. Let me show you a little visual representation of what he said, and I'll just read his words to you while this plays. So he said, "Shut yourself up on a large ship, and there procure gnats, flies, and other small winged creatures. He said, let a bottle be hung up, which drop by drop lets forth its water into another narrow-necked bottle placed underneath. Then with the ship lying still, observe how the winged animals fly with like velocity toward all parts of the room, how the distilling drops all fall into the bottle placed underneath. Then, he says, having observed all these particulars, make the ship move with whatever velocity you please." So here it is, the ship is going into motion, and he says that so long as the motion is uniform, by which he means constant velocity, you shall not be able to discern the least alteration in all the forenamed effects, nor can you gather by any of them whether the ship is moving or standing still. That is
right. So material objects gain velocity in more than one direction, in a sense, is the argument. They can be moving this way and they can be moving that way. So you can move the ship and everything basically stays the same in terms of everything going this way or any other way. And that's sort of how you understand everything being thrown into gravity, is that the two forces don't mix. the ball, when you throw it, the velocity this way isn't interrupted by the velocity down, and the velocity down isn't interrupted by the motion this way. You fall at the same rate in the gravity, and your velocity of the baseball stays constant, except for air resistance.
Is the very same idea that constant velocity motion cannot be detected. It has no impact on your observations. Old idea. Back with Galileo.
Except when you look out the window. I mean, you know, it depends. So again, it's just this stupid rule. They just apply a rule that just sits there and confines you and prevents you from doing the experiments that would tell you who's moving and who's not. And again, the point is you can't make a light clock. So if we could make a clock that actually worked at the speed of light, or a mechanism that functions at the speed of light and creates a discrete enough object, you would see that that object, okay, ends up being a standard. It ends up being something you can watch and watch everything else relative it move.
So where then does Einstein come into this story? Einstein's new contribution is to say that among the four named effects that Galileo was talking about, he was just talking about the gnats and flies and the water dropping into the bottle placed underneath, that those things would not change.
Okay, this is fun. My name is Dana. I'm on Brilliant.org and I'm learning data science. I work in marketing. It's very data driven, and I really don't want to be the only one who doesn't understand some of the simple things. On Brilliant, you're learning through doing, and then you check your...
It's really fun to plug numbers in and see what kind of results we get. So I've done that on the next slide.
Okay, so why have we not found aliens? How the hell did it do that? Exactly. All right, anyway, something went wrong. But won't bother paying much attention. Oh, bubble puppy, I don't really... So in this boat example, you're saying we still cannot detect changes if the boat were accelerating. No, if you're accelerating, you can. So Galileo was saying, once you reach a velocity, so you sail to a certain speed, and then it's a constant speed, and then you let your little flies loose and your water drops. But yeah, while you're accelerating, you would see the water miss. You know, that's a real possibility. It's really, you know, frankly not true, because you know, you're not doing the right experiment to detect acceleration. You'd have to have something moving in the direction that you're moving to detect the acceleration, because you're accelerating the emitter, and with water drops you're also going to accelerate the water drop in the direction of your acceleration, so the drop isn't going to fall straight. But this is the catch, right? It just depends on the circumstance, and you're saying, well, I can't figure out an experiment. Well, there are experiments. I mean, you know, it just, you have to have the liberty to do them. But if they say you can't look out a window and you can't put anything outside the ship, well, then it gets harder. But in the example, wouldn't each piece be accelerated at the same rate, and therefore the drops remain in sync? Well, the point is you're accelerating the emitter of the drop. So when the dropper is being emitted, the drop, the bottle's accelerating. So it's going to give the acceleration to the water. So the water is actually going to go in two directions. It's going to go down, and it's also going to go forward. So it's going to land in the bottle that's moving forward, because it's basically throwing the water forward. But light doesn't work that way. You can't give light two momentums. See, the water drop, you can give it two momentums. You can be both throwing it, you know, just like you can throw a ball off a train or something. I mean, there's lots of examples where you throw it this way. You know, you give it momentum sideways, perpendicular off the train, but the train has a velocity of 30 miles an hour in a direction. So the ball is going to be going two directions. It's going to be going 30 miles an hour that way, right? Plus the, whatever, 30 miles an hour forward, you threw it. So it's got two different velocities, and the two of them aren't going to add in a complete way. They're just going to stay in the ball, and the ball is going to take the right course, but it still has both of the velocities. It has your velocity, the momentum you gave it, and it has the momentum the train gave it. So, thanks for the comment. See if anybody else has anything to say, and we'll save the rest for some other time. It's strange. It's that stupid button, I guess, that somehow I hit.
Back with Galileo.
The
So
wrong
where then
button.
does Einstein come into this story? Einstein's new contribution is to say that among the four named effects that Galileo was talking about, he was just talking about the gnats and flies and the water dropping into the bottle placed underneath, that those things would not change if you go into motion so long as it's uniform. Einstein added something to the list.
So he shouldn't say if you go to into motion, right? Because that's acceleration, going into motion. So it's sort of, you know, that isn't a very good way of describing it for a rehearsed, scripted thing. He should have done a little better than that.
Einstein added to the list of things that would not change, he added the speed of light. This is the surprising new insight.
All right, so I don't, you know, whenever people say this is surprising, you're just like wondering, why is it surprising? Something has to be going slower than instantaneous, right? I mean, everything, obviously none of our and around us is going instantaneous. So clearly everything has to be lagging behind instantaneous. And why wouldn't we think light's doing the same thing? Why would we think it's instantaneous? Because if it was instantaneous, wouldn't it cause everything else to sort of be instantaneous? If all the forces acted instantaneously, well then wouldn't everything just happen now and it's over?
Of Einstein, let's see what it means.
All right, so we'll do that next time and such. But yes, there's no, you know, I don't, like I said, I don't see why anybody would think, I mean, I don't think it shocked anybody back in Newton's day when they started talking about the possibility that light moves at a specific speed. You know, it wasn't some big surprise, and we didn't need Einstein to show up certainly 300 years later to say, oh, I'm pretty damn sure it does. I think a lot of people already were pretty damn sure it was a constant speed and that it was moving really fast and that nothing's going faster. I think they all had pretty much figured that out. So to me, it's not miraculous that he would propose a non-variable speed of light. That's, you know, and a limit that you're not going to get anything go faster than. But the real point is by Maxwell's time, they should have already changed the verbiage. We should have already been saying the speed of force, because Maxwell detected actually the speed of electricity and, I mean, induction. So magnetic induction is what he predicted the speed of, and the argument is that you can do this induction thing at lots of frequencies, including the frequencies that include light. So it was really just the speed of induction. So it really should just be called the speed of force, because now we know that gravity does the same thing and that everything, this is the speed that forces move at. So as soon as you get to Planck-size particles or Planck-size quanta of energy, it's all moving the same speed. The quanta of energy that make up the magnetism or the charge or the electricity or the light, it's all the same quanta moving a speed and gravity. So if they would have been saying the speed of force, you know, 150 years ago, that would have been very helpful. Well, it's because it's 200 now. Nearly. Alright, so 1 minute warning. So if somebody doesn't have anything, if there's no comments or questions, I will be on my way. Alrighty then. Yeah, okay, I shorted you, 30 seconds, but that's how it goes. Yeah. So anyway, till the next time and such, and so forth and whatnot. Well, it might take me 20 seconds to get out of here, as I like to clean up before I go and such. So till the next time and such. and so forth and whatnot. That'll do, pig.